Welcome back to the review of energy balances. We looked at all the fundamentals, we looked at the terminologies which are used in energy balances, we also looked at the procedures, objectives and all the fundamental concepts like how to account for different things like phase change. We also looked at how solutions and reactions are uniquely treated. We looked at all the basics which are required for performing energy balances. So, this review gave a short and a brief explanation on how energy balance problems can be done. So, now we will try to apply these principles and perform quite a few example problems. So, these problems have been chosen so that they are reasonably complex. So, this gives a perspective of how energy balances can be done for complicated systems, and we will be looking at these problems which are probably a lot more intense than the example problems we have chosen. So, this session is for us to get a feel for how energy balance problems can actually be approached when you have reasonably complicated systems. So, we will talk about 3 different example problems. So, the first example problem which we are going to start with is here. A vapor containing 9.1 weight % water and the rest toluene is condensed and cooled in a process shown in the figure. For every 100 kilograms of coolant C charged into the system, 27.5 kilograms of vapor enters the condenser. You are asked to calculate the temperature of the exit coolant that leaves the condenser, the mass of the cooling water required per hour. So, these two things have to be calculated. So, the problem also gives us the data for Cp, boiling point and the heat of vaporization for different components. So, you have water liquid with a Cp of 4.2 and a boiling point of 100 degrees Celsius and heat of vaporization as 2260 kilojoules per kilogram. So, you have water vapor where the Cp is given as 2.1 kilojoules per kilogram degree Celsius, and C7H8 is toluene. For toluene liquid and gas you have the Cp values given, and for the toluene liquid you also have the boiling point and the heat of vaporization which has been given. So, C is the coolant which is being used in the first unit, which is the condenser. So, the Cp for that is also given. So, now look at the process. You actually have 2 units in this process. So, until now we have always been using a single unit system when we performed energy balances. Primarily we have focused energy balances done only on one unit, even when there are multiple units. In some examples we had energy balances in one and the other one was only material balance and so on. So, here these are 2 systems where both are involved in energy balance operations. So, we will look at this process, and what you see here is a feed which contains 9.1% water. It is a vapor feed containing 9.1% water which is entering at 150 degrees Celsius. So, and you have a coolant which is coming in at 50,000 kilograms per day and 20 degrees Celsius and entering the condenser. So, the vapor gets cooled because of the action of the condenser. So, I have the coolant and you have a saturated liquid containing both water and toluene which is coming into the stream F, which is leaving the condenser. The coolant also leaves the condenser at a temperature of T, and the saturated liquid then enters into a separator where it is actually coming in contact with liquid water at 20 degrees Celsius, and water leaves the system as liquid water at 60 degrees Celsius. The saturated liquid is further cooled to get liquid which is at 40 degrees Celsius. So, this would be the liquid which contains both water and toluene. So, as you can see, the boiling point of water is 100 degrees Celsius and boiling point of toluene is 111 degrees Celsius. So, in both cases it is actually going to be only liquid, and we are not worried about the pressure here. For vapor phase we will assume ideal gas behavior, and for liquid phase we will ignore the effect of change in pressure, because the change in pressure for such process here would be very small, and the effect on enthalpy for such small changes in pressure can be ignored. So, taking that into account, this is the flow chart we have, and one thing we need to be clear about is what is the heat which is being transferred between the system we are interested in and the surroundings. So, we can have different systems which we can choose here. So, we could either choose the condenser as a system, or the separator as the system, or the overall system. These are the 3 possible systems that can be chosen, and for each of these we would have to understand that there is no heat which is going to be lost between the system and the surroundings, because here there is not you have not been given any heat which is being transferred to or from. So, whatever heat is being transferred, for example, in the condenser would be only the heat transferred between the coolant and the vapor. So, heat is lost by the vapor which is coming in and gained by the coolant which is coming in. Similarly, in the separator as well, you would have heat lost by the saturated liquid, therefore, it is leaving at a lower temperature, and heat is gained by water, and it is leaving at a higher temperature. So, this is an assumption we can make based on the system we have. So, each of these do not have any heat lost to the surroundings which is outside the system. Heat transfer is happening only between the coolant and the vapor, or coolant and the liquid. So, in the second case the coolant is the water. So, with this information, let us now look at solving this problem. So, here is the flow chart. We have the information that we have entered. So, you have 50,000 kilograms per day of coolant coming in, and we know that for every 100 kilograms of coolant you have 27.5 kilograms of vapor which is being fed. So, let us first perform the basic material balance which is required. So, as I always say, material balance is the first step for any energy balance problem. So, let us perform the material balance to get the feed input. So, we have 27.5 kilograms of vapor fed per 100 kilograms of coolant. So, we actually have 50,000 kilograms per day of coolant coming in, which means the amount of vapor which is the mass of vapor which is fed would be 27.5 divided by 100 times 50,000. So, this is equal to 13,750 kilograms per day. So, this is the mass of vapor which is being fed to the system. So, we know that out of this 9.1% is water. So, and the rest is toluene, which would be 90.9% is toluene C7H8. So, now we need to calculate the mass of water and toluene which is coming in, so that we will know the mass of water and toluene which is leaving through the F stream here. So, mass of water would be 0.091 times 13,750 kilograms per day. This is the mass of water entering the system, and mass of toluene entering the system would be 0.909 times 13750 kilograms of toluene per day. So, these can be calculated as water equals 1,251.25 kilograms per day, and toluene is equal to 12498.75 kilograms per day. So, now that we have the mass of toluene and water entering, we can start looking at the energy balance aspect. So, what do we do for the energy balance? So, we have to write energy balances to identify two things. First one is to identify the temperature T2, and then the second one is to identify W, which is the mass of water which is being fed in the second system. So, for finding out temperature T2, we can choose a system which would be only the condenser. So, let us choose this as the system of interest. So, for the condenser, let us start writing the energy balance equation. So, the condenser is an open system because you have material crossing the system boundary. So, the equation would then become Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. As there is no change in kinetic and potential energy or moving parts, these terms go to 0, As I had already mentioned, the process does not have any any heat being lost between the system and the surroundings. So, Q dot will also be equal to 0, giving you delta H dot equals 0. So, now that you have delta H dot equals 0, we can write the expansion for H dot and identify the value for the temperature. So, here you also have only constants given as Cp values, which means you would not have a very complex polynomial which we used to end up with when we calculate temperature. So, usually we would have a third order or a fourth order polynomial which would be difficult to solve. Here it would be a simple linear equation which can be solved. So, let us try to do that. So, for doing that we first need to identify the reference states so that we can build the enthalpy table. So, let us look at what could be the reference states. So, here we are not going to be using any enthalpy table as such like steam tables or anything. So, here we are going to use the Cp values which have been given for calculating enthalpy, which means we can actually use either the inlet or outlet conditions. So, I have chosen to use the inlet conditions for the vapor and the coolant as the reference states. So, which means the reference state for toluene would be vapor at 150 degrees Celsius, water would also be vapor at 150 degrees Celsius, and you have the coolant which is coming in at 20 degrees Celsius. So, these are the information we have, and now let us build the enthalpy table. So, the enthalpy table would have in toluene, water and coolant, and we will have M in dot, H cap in, M out dot and H cap out. And toluene coming in, we had calculated it to be 12,498.75, and water coming in we have calculated to be 1251.75. Coolant, it has been given as 50,000, and so whatever is coming in is also leaving the system. There is no change when it comes to the chemical composition of the system, it is only the phase which is being changed. So, we will have 12,498.75 kilograms of toluene leaving per day, 1251.75, sorry, this should be 1251.25 kilograms of water leaving per day, and C is 50,000 kilograms of coolant leaving per day. So, now which of the enthalpies do we have to calculate? We had identified the inlet condition as the reference state, which means these enthalpies which are present for the inlet streams would all be 0. We would only have to worry about the enthalpies for the exit streams, which would be H1, H2, H3. So, we need to now calculate H1, H2 and H3. Let us first look at H1 cap. So, what is H1 cap? So, H1 cap is nothing but toluene vapor at 150 degrees Celsius, which is the reference state, forming the exit condition which is toluene liquid at 90 degrees Celsius. So, the process is toluene which is from vapor 150 degrees Celsius goes to toluene which is a liquid at 90 degrees Celsius. So, here you have both temperature and phase changing, which means you have to build a hypothetical path. So, the path can be toluene vapor at 150 degrees Celsius is cooled to toluene vapor at 111 degrees Celsius. So, I choose 111 degrees Celsius because that is the boiling point of toluene, and we have the information about the heat of vaporization at 111 degrees Celsius which has been given to us in the problem. So, if you look at the problem statement, you can see that the toluene boiling point is 111 degrees Celsius and the heat of vaporization for toluene at that temperature is also known. So, based on this I have chosen 111 degrees Celsius for the change in phase, and from here it goes to toluene liquid at 111 degrees Celsius, which would be the saturated liquid at 111 degrees Celsius. From here it is cooled to 90 degrees Celsius. In the first step you have delta T, and in the second step you have delta phi, which is a change in phase, and the last step you again have delta T, which is change in temperature. So, using this we can calculate H1 cap as follows. H1 cap would be equal to integral 150 to 111 Cp of toluene vapor dt plus delta HV cap negative of it for toluene. So, this we are using the negative of heat of vaporization because you have condensation reaction happening, condensation process happening here, not vaporization. So, it will be the negative of heat of vaporization plus integral 111 to 90 Cp of toluene liquid dt. So, now that we have this as the values for H1 cap, let us calculate H1 cap. So, H1 cap is equal to integral 150 to 111 times 1.3 dt. So, we are getting the Cp values from the table which was given to us in the problem minus 230. So, the value for heat of vaporization can also be obtained from the table plus integral 111 to 90 Cp of toluene liquid is 1.7 dt. So, using this we would end up with H1 cap as minus 316.4 kilojoules per kilogram. So, this gives us H1 cap. Now, we need to identify H2 cap. So, H2 cap is again the change in enthalpy for water from the reference state which is 150 degrees Celsius and vapor. From there water goes to, so this is water at this condition, goes to the outlet condition which is 90 degrees Celsius liquid water. So, from here to here you have both change in temperature and phase. Again you build a similar hypothetical path where it is first cooled to the boiling point of water which is 100 degrees Celsius and vapor, and from here it is it changes the phase to form 100 degrees Celsius liquid. So, there is a condensation reaction, condensation process, and from here it is further cooled to get 90 degrees Celsius and liquid water. So, the first step is delta T, second step is delta phi, and the third step is delta T. So, this is the process we can build. So, using this we would again be able to calculate the H2 cap. So, H2 cap can be calculated as follows: H2 cap equals integral 150 to 100 Cp dt plus negative of heat of vaporization for water plus integral 100 to 90 Cp dt. So, the first Cp would be for water vapor and the second Cp would be for water liquid. So, now we have the values for Cp, values of Cp for water vapor and water liquid from the problem. So, using that we will get 2.1 times 100 minus 150 minus 2260 plus 4.2 times 90 minus 100. So, this would give us a value of minus 2407 kilojoules per kilogram. The next thing to calculate is H3 cap. So, for H3 cap you have the coolant which is actually being cooled from, so which is being heated from 20 degrees Celsius to temperature T2. There is no phase change for the coolant which has been given. So, we will only look at the change in temperature. So, it is a single step process where it is heated from 20 degrees Celsius to a temperature of T. So, Cp of coolant dt. So, Cp of coolant has been given as 2.1. So, this would just be 2.1 times T minus 20. So, we have the general energy balance equation simplified to delta H dot equals 0. So, now we can substitute the values for these H1, H2 and H3, and we already know the masses of the toluene, water and the coolant which are coming in. So, your equation for delta H dot will actually become 12,498.7 times minus 316.4 plus 1251.25 times minus 2407 plus 50,000 times 2.1 T minus 42 equals 0. So, this equation will then simplify to form 1,05,000 times T equals 9066363.25. So, from here temperature T is calculated as 86.3 degrees Celsius. So, the coolant is actually heated from 20 degrees Celsius to 86.3 degrees Celsius, so that the vapor which is coming in at 150 degrees Celsius can be cooled to form a condensed liquid at 90 degrees Celsius. So, now that we have the first part of the problem solved, let us move on to the second part of the problem. For the second part of the problem, we have been asked to calculate W, which is the mass of water which is fed in the cooler. So, we already have the information about the liquid which is entering the cooler, and it would be the same as the liquid which is leaving the cooler as well. So, having that information, we can now start writing the energy balance equations. So, again here the equation would be for an open system, Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. Again the equation will simplify to form delta H dot equals 0, because you do not have any change in kinetic or potential energies or shaft work, and as we already discussed, the process does not have any energy exchange between the system we have chosen, which is the cooler, and the surroundings of this system. So, this means delta H dot becomes 0. So, we now have to choose the reference states for which we can build the enthalpy table. So, let us choose a reference state. So, here I have chosen the inlet conditions for the liquid which is entering as the feed for the cooler as the reference states. So, this means toluene at 90 degrees Celsius and liquid and water at 90 degrees Celsius and liquid have been used as the reference states. So, you also have water which is coming in at 20 degrees Celsius. So, we will have to account for that separately. So, here you would have to build an enthalpy table. So, what we need to do here is we actually have to list water twice, because you have water coming in and leaving in two different streams and the conditions are different. So, we need to write water entering through the liquid feed for the cooler as one stream, and water which is entering through to the cooler as a coolant as another stream. So, what happens is the table would actually look like this. So, you would have toluene and you would have water which is the feed, and you would have water which is the coolant. So, these three are the components which are there in the system, and you can have M in dot H cap in, M out dot and H cap out. So, M in dot for toluene would be 12,498.75, water through the feed liquid would be 1251.25, water which is coming in through the cooler would be through the coolant stream would be W, and the same would be the values for the outlet streams as well. So, you have 12,498.75, 1251.25 and W as the mass flow rates out. So, now let us look at which of the enthalpies would go to 0. So, we had taken the toluene at 90 degrees Celsius and water at 90 degrees Celsius as the reference states, which means these two will go to 0. So, the stream where water is entering as the cooling water would be having some enthalpy difference from the reference state. So would the other streams. So, we would have to calculate 4 different enthalpies here. However, here there is no phase change which we have. So, we would not have to build any hypothetical paths, we just have to account for change in temperatures. So, once we have H1 cap, so H1 cap is basically water liquid at 90 degrees Celsius, which is the reference state, is being cooled to the cooling water condition, which is water at 20 degrees Celsius. So, this process would just be a change in temperature. So, you have Cp dt, integral Cp dt from 90 degrees Celsius, which is the reference state, to 20 degrees Celsius, which is the inlet condition, and this would be equal to 4.2 times 20 minus 90. So, giving you a value of minus 294 kilojoules per kilogram. So, H2 cap would be equal to integral Cp dt from 90 to cooling to toluene is leaving at 40 degrees Celsius. So, you have 40 as the temperature for the outlet stream. So, this would be equal to 1.7 times 40 minus 90, giving you a value of minus 85 kilojoules per kilogram. So, now we can calculate H3 cap. So, H3 cap is for the process where water at reference state of 90 degrees Celsius in liquid is being cooled to the water liquid which is leaving through the product stream P which at 40 degrees Celsius. So, the process is integral 90 to 40 Cp of water dt. So, you have a cooling from 90 degrees which is the reference state to 40 which is the exit condition for water. So, this would be 4.2 times 40 minus 90 giving you a value for H3 as minus 210 kilojoules per kilogram. H4 cap would be integral 90 to 60 Cp of dt with Cp being the Cp of water liquid. So, here you are looking at water which is the cooling water leaving the system. So, now we have taken the reference state for water as 90 degrees Celsius. So, from there it is being cooled to the outlet stream which is 60 degrees Celsius. So, you have integral 90 to 60 Cp dt. So, this becomes 4.2 times 60 minus 90. So, which is equal to minus 126 kilojoules per kilogram. So, we had already simplified the general energy balance equation as delta H dot equals 0. So, substituting all these values for H caps and the masses which we have, we would have 12,498.75 times minus 85 plus 1251.25 times minus 210 plus W times minus 126. So, these are the enthalpies for the outlet stream, and for the inlet stream you only have the water cooling water which is entering. So, which would be minus W times minus 294, this is equal to 0. So, this equation can then be simplified to get 168 W equals 1325156.25 giving a value for W as 7887.8 kilograms per day. The problem asks us to calculate the water mass which needs to be fed per hour. So, dividing this by 24 we would get W equals 328.66 kilograms per hour. So, this is the rate at which water needs to be supplied to the system for getting the required cooling. With this we have actually looked at a simple example problem where we had a multi-unit process where both the processes had energy balances that can be performed, and we had a system where there was no reaction as such, there was only phase change which was happening, and we were looking to perform the energy balances required to calculate the temperature of an exit stream and also the mass which is required for an inlet stream to get the desired levels of cooling. So, with this we have performed one example problem for the energy balance review. In the next lecture we will look at another example problem which will again try to apply the fundamentals which we looked at during the review, and we will perform this calculations in the next lecture. Thank you.